All right, hello. Okay, so let's lower the levels a little bit. Okay, this is still clipping. Okay, so great. I'm doing another stream tonight of Advent of Code because it looks like streams are doing better than normal videos. So yeah, we're gonna. Why is this still clipping? Maybe I need to point it further away. Okay, I apologize for all the high high levels. Okay, so hopefully this should be fine. This is a really sensitive mic. I should turn that sensitivity down. Here, maybe I'll do that right now. Okay, but anyway, the puzzle's coming out in 4 minutes, so yeah, I'm gonna be doing it. Okay, so what if I just I'm turning the microphone away. Okay, I apologize for all of this. Okay, so looks like it's doing pretty good. What if I turn it even further? So now it's really further. Now it's really far away. Okay, so this should be good. Okay, hello everyone. Today we're going to be doing another day of Advent of Code. It's day 10, so special. I figured we do a special video, so it's a stream now. So yeah. Okay, I'm also gonna start recording just in case I want to make a short video. So never forget to drink your water as well. So yeah, we're gonna be drinking water all throughout this Livesolve. There will be timestamps in the description if you want to skip to different parts of the video, so like the different explanations, because you probably don't want to watch me code if you're watching this after it's live. So yeah, there's going to be a GitHub repository linked in the description if you want to check out the code. There's going to also be a playlist of all past and hopefully future videos. That's also going to be linked in the description. Okay, here. How about now? Okay, this is much better. Okay. I will also be. These explanations. I noticed that these explanations are really like high level. I think I need to go more like low level into the actual implementation when I'm doing these explanations, because it looks like that's what more people need help with. So yeah, I'm going to be going really into the code, less about the high level stuff, because I figure, the high level stuff is for all harder problems, like Usico, gold, silver, that hard stuff. So yeah, these puzzles aren't that difficult. They don't really require any algorithms. And like the hard part about hard programming problems is more like figuring out how to actually do it, not implementing it. But I think for Advent of Code, it's more implementing it and less like finding out how to do it. Although finding out how to do it is also part of it. So yeah, we're gonna have to look at that. Oh, okay, you can see audio levels. So I was just looking at that, trying to get that figured out. So I'll also edit this video on the YouTube editor, just to like get a feel for it and see how it works. So I know how to like use it. So okay, the puzzle's coming out in 1 minute. Why don't we set up our files? Okay, and I know I shouldn't be putting periods in the names, and I should be using underscores. So I'll fix that in the future with some kind of script or something. Alright, so we are going to start doing this soon. Okay. Oh wait, did I not push this to GitHub? Okay. Okay, my apologies. So you have that now. Wait, oh. Okay, I also pushed this. So that's pretty unfortunate. Okay, but anyway, the puzzle's coming out soon. We might as well do it. Okay, 19 seconds. Wait, actually, I should probably pull out some stats just to see how many people are actually watching. Yeah, okay, it doesn't look like a lot of people are watching. Let's bump at the chat, and let's put the chat in the corner. And I know it's like pretty late for a lot of you in a different time zone from me. So, yeah, we're just going to put this down in the corner over here. Alright. Okay, I know the puzzle's already out, but okay, hopefully that looks good. And so far nobody's been using the chat, which is fine. better close that to reduce bandwidth. Okay. Also, I figured out how to get my bandwidth internet upload to actually work better. It was to put my computer up on my desk instead of below my desk. So, simple solution. All right. So, day 10. I'm going to be explaining this and doing it live. All right. Day 10. Adapter array. Patched into the aircraft's data port, you discover weather forecasts of a massive tropical storm. Okay, so that's probably where most of this year is going to be spent. Before you can figure out whether it will impact your vacation plans, however, your device suddenly turns off. Okay, how is this thing still clipping? This doesn't make any sense. Further away? Okay, I don't know if it sounds really distant now. Here, I'm just going to go off camera for a bit. I'll edit this out, but just to fix the sound settings. Okay, my apologies. I'm back now. Hopefully this should be better. It should be clipping less. The audio levels are probably a little bit softer, but okay, that's fine. Okay, oh. Hello. Okay. We have some stuff in the chat. Hello, Michael. I'm not sure which Michael this is, because I know two Michael L's. But I will just respond. Hello, I am in my room. And the background, well, it's just the background of my room. All right, nice. Some very high quality user interactions here. All right, okay. Let's keep reading. You'll need to plug it. Oh, its battery is dead. You'll need to plug it in. There's only one problem. The charging outlet near your seat produces the wrong number of jolts. Always prepared, you make a list of all the voltage adapters in your bag. Each of your voltage adapters is rated for specific output voltage, your puzzle input. Any given adapter can take an input of 1, 2, or 3 jolts lower than its rating and still produce its rated output voltage. Okay. In addition, your device has built-in voltage adapters rated for 3 jolts higher than the highest rated adapter in your bag. Okay, wait. If your adapter list was 396, your device's built-in adapter would be rated for 12 jolts. Okay, wait, I haven't read the problem before, so reading this, I actually probably need to read this a little bit more to understand, but let's just keep reading. Treat the charging outlet near your seat as having an effective voltage rating of 0. Since you have some time to kill, you might as well test all of your adapters. Wouldn't want to get to your resort and realize you can't even charge your device. If you use every adapter in your bag at once, what is the distribution of voltage differences between the charging outlet, the adapters, and your device? Okay, and now they give an example, which should help me a lot. For example, suppose that in your bag you have adapters with the following voltage ratings. 16, 10, 15, okay, all of these. With these adapters, your device's built-in voltage adapter would be rated for 22 jolts, 3 higher than the highest rated adapter. Because adapters can only connect to a source 1 to 3 jolts lower than its rating, in order to use every adapter, you'll need to choose them like this. Oh god. I'm actually going to reread some of this, because now I realize that when I'm reading the problems, it probably doesn't make a lot of sense for all of you. So, my apologies. Okay, let's just continue, and I'll reread it later and edit that out. Okay, because adapters can only connect to one... okay, you'll need to choose them like this. The charging outlet has an effective rating of 0 jolts, so the only adapters that connect it to it directly would need to have a voltage rating of 1, 2, or 3 jolts. Okay. Okay. From your 1 jolt... What? Okay, so it looks like we need to go in steps of 1 or 3, but I don't know exactly how that works. So let's keep going. In this example, when using every adapter, there are 7 differences of 1 jolt and 5 differences of 3 jolts. Okay, I see. Larger example, okay. For a China chain that uses all your adapters to connect the charging outlet, all of your adapters, okay, to connect the charging outlets to your device's built-in adapter and count the voltage differences between the charging outlet, the adapters, and your device. What is the number of 1 jolt differences multiplied by the number of 3 jolt differences? Okay, that's interesting. I think from the example, I'm getting a better idea of how this works, but I will have to reread this to understand. Okay. Any given adapter can take an input of 1, 2, or 3 jolts lower than its rating. Okay. Your device has a built-in... Okay. I see where this is going. So the device has a voltage output. A voltage input that can take 3 higher than the highest rated adapter in the back. So, okay. So we need to make a list of all these voltages, order them in steps of 1 to 3, 1 or 3, and then the highest one plus 3 is the voltage rating of our device. Okay. Okay, I see. So it goes 0 to 1 to 3, 0 to 1 to 4 to 5 to 6, 7. Okay, I think where this is going. I see where this is going. So I think what we have to do is we have to actually sort this, because if we're going to have to use all of them, I don't think we can, we can't go like from 4 to 7 and then go back to 6. I don't think we're allowed to do that. So I think I know where it's going. I think we have to sort this, and then after sorting, we just count the differences. And hopefully that should work. So let's just do that. Okay. Whoa. What was that? Okay, I have to make this... Okay, and then for all the numbers, I think we should just make a function to... I think we should make a function to make it easier. So, let's count differences, and then we just take an arbitrary input. So voltages. Okay, and we'll want to sort these. Joule. So we want to sort these, and then we want to go through all these and count the differences. Okay. And we'll probably want to go to -1 because we don't want to count. We want to count the differences, and there's one less of the differences then, because we're going to look at the one ahead and count. Whatever. Okay. Okay, so in this line, we're basically looking at the difference between the voltage in front and the current voltage. And at the beginning, we sorted this to make sure that we don't skip any adapters, because we have to use all of them. And sorting is the best way to do that. Well, actually, the only way to do that. So, okay, and then we can return ones times, well, why don't we just do that? Okay, so now we want to actually have our input. Okay, so that's our list of integers. We just convert it to all integers, and then we want to, yeah, okay. You know, using VS Code is so much easier than using Notepad++ because it auto-completes stuff for you. Okay, no doubt we're going to have some kind of errors here. Oh, okay. Wait. 2015? Now that's kind of sus. That's kind of sus. Okay, yes. Hello, Brian. VS Code, yes. Well, I mean, it depends on what you're doing. If you're making, in my opinion, if you're making any kind of software applications, you should use VS Code. If you're doing competitive programming, you should probably use Notepad++. So in general, VS Code, yes, it's probably better. Okay, so I got 2015. Ooh, it's not the right answer. Okay, so I think what we should do is look at this input and see if it's right. So let's just put in a smaller input. This is the third time I've gotten something wrong. So, not a lot. 6 and 4, okay. 7 differences of 1 joule in 5. Okay, it looks like we're missing 1. Oh, we forgot to count. We forgot to count the 0 case and the case that goes to. Okay, yeah, because there's the outlet in the seat, which has a voltage of 0, and then there's your device, which has a voltage of the maximum voltage in your adapters plus 3. So we're actually going to have to modify this. We're going to do 0 plus voltages plus the last element plus 3. And this Python syntax basically just adds all of them together to make a new list. And I will be explaining all of these afterwards, so don't worry. Wait, is it really only 97 lines long? Whew. I should also probably include comment. Okay, 2046. I think this should be right. What? It's the right answer for someone else? You might be logged into the wrong account or just unlucky. Oh my god. It's the right answer for someone else, but that's not because I copied it from someone else. Okay. This is the first time I'm getting this. Okay. That is super weird. I think we need to go back to our short input and because we didn't actually test this. 28 7 and 4. Okay, so it's wrong. Or you know what we could do? You know what we could do just to cheat? We could do the voltages and then we can add 1. Alright, and that should make everything perfect. So 7 times 5. Okay, and let's actually test a larger example while we're waiting for our 1 minute to pass. That would be 22 and 10, which is correct. Okay, so we just did a little bit of implicit programming. Okay, 220. That doesn't make any sense. Oh yeah, we're not using our big input. Okay, so hopefully this should bring us the right 2112. Okay, that's the right answer. Okay, now I'm going to explain this in full detail. Okay, let's go. So, this code is pretty short, but I'm going to go into a lot of detail here because I think that's what you all want. You all who are watching the video want. Okay, so I'll just give a high-level overview first. You can ignore this, skip ahead if you want to like actually see the details. So, but you probably need to understand this first. So, the idea is to sort all of the adapters because maybe I should simplify the problem first, actually. Okay, so basically we have a bunch of adapters, and each adapter has a rating. And the rating is how many voltages it can output. But the adapter also needs an input, right? So each adapter has an output and an input. Its output is just its rating. Its input can be anything ranging from its output -3 to its output -1. And so, for example, if we have something that's 16 voltages of output, it can accept anything from 15 to 14 to 13. All right, those are all valid inputs for this adapter. And then we at the very ends of the adapters is going to be uh, the outlet in the seat, which has a voltage of 0, and then our device, which has a voltage of 3 plus the highest output adapter. So if our highest output adapter was 9, then our device would have a voltage input of 12. So basically, we just need to form a long chain of these adapters that starts from 0 and goes to our device's voltage. And we need to make sure that we use every single adapter. So the first thing that we want to note is that these adapters are going to be increasing in voltage, because each adapter can only have an input that is smaller than its rating. So obviously, they're going to be increasing as we go from the socket to our device, right? And because they're increasing, there's only one order that's going to use all of these adapters, and that's going to be the sorted order, because it has to be increasing and it has to use all of them, and that's the definition of the sorted order. So we're going to sort all our adapters. So I guess in this example, I could actually print this out. So why don't we do that? Okay, so I'm gonna print voltages. Okay, so I know this console is really small. I don't know if I can increase it. Okay, I don't know if I can increase the size of this any bigger. But you can see here that in this example, the sorted order is going to be 1, 4, 5, 6, 7, 10, 11, 12, 15, 16, 19. And this is just our first adapter is 1 for our last adapter, which is 19. The socket outputs to the 1 adapter, and then the 19 adapter outputs to our device. And then after that, we know the sorted order, so we just have to count all the differences in between, which is what the problem asks us to do. So for example, this would have differences of like 3, 1, 1, 1, and so on, because 1 to 4 is 3, 4 to 5 is 1, 5 to 6 is 1, 6 to 7 is 1. We need to count up all these, count up the number of 1 differences, and then count up the number of 3 differences, and then multiply them together. So that's the high-level overview. In my videos, I would usually stop there, and I wouldn't really go into the code, but I'm going to go into the code this time because that's probably important. Okay, so let's explain the code. At the very beginning, we just take in our input. All right, okay, and now we have a function which takes in a list of voltages, which would be something like this list over here, 16, 10, 15, 5, 1. It doesn't have to be sorted. It just takes in the raw input. After that, we sort it, as I explained earlier, because there's only one order for the adapters to go. I don't actually need this line. Okay, and then we initialize a few variables to count the number of 1 differences and the number of 3 differences. And these differences, basically in the problem, is just the jumps between the adapters. This is going to be our tally. It's going to increment through while we're counting. Okay, and now our voltages are sorted. So I should probably print all this out just to make it more clear. Okay, so now we have a for loop, and our for loop basically just loops through all of the adapters in their sorted order. And the purpose of this for loop is to count the differences between the adapters. Okay, so I'm actually going to print this out. Okay, we can see in our example, this is really small, I know. I'm going to have to look up how to make this bigger. But okay, so we have our sorted list as we saw earlier. In this for loop, we're comparing every consecutive pair of adapters. So we can see here it's 1, 4, 4, 5, 5, 6, 6, 7, 7, 10, and so on. And we can look at the difference between these consecutive adapters. And their differences, if it's 1, then we're going to increment our count of the 1 differences. If it's 3, we're going to increment our counter of the 3 differences. And then that's basically it for the for loop. At the end, we return 1s plus 1 and 3s plus 1. Oh, I actually messed up there. I messed up there. Yeah, I really shouldn't have that here. Ooh, that was a close call. My apologies. Hopefully this should be right. Still. Okay. Oh my god. Okay, sorry. Just ignore me for a second here. I made a mistake. You can just ignore the mistake, but it was fine. Okay, so after that, at the very end, we return our count of ones and our count of threes. We can say that our count of ones is just our count of ones, but we have to increment our count of threes by 1 because inside this list we are not considering our device, and our device actually has to be at the end of this list because it has the greatest voltage, right? So at the end of this list, there's going to be a jump of 3 from our last adapter to our device because that's given in the problem. So we need to add 1 to the count of the jumps of 3. So we just return that, and then multiply them together, and that's it. For these lines, this is just basically parsing our input and determining our output. This line, this is pretty standard in every single problem. You basically just go through the input, turn it all into a list of integers using something called list comprehension. Oh. Hello, Emily. Okay. Yeah, this is called list comprehension. We just go through all of it. We turn all the strings into integers using the int function. And then at the end, we just call our function and multiply the ones and the threes. And hopefully that made sense because I went into more detail here. Okay, part 2. Okay, to completely determine whether you have enough adapters, you'll need to figure out how many different ways they can be arranged. Ooh, okay. Every arrangement needs to connect the charging outlet to your device. The previous rules about when adapters can successfully connect still apply. In the first example above, the one that starts with 16, 10, 15 supports the following arrangements. Okay, so basically we just don't need to use all of the adapters here. Okay, who's getting a shout out? I shouted out Brian earlier. Okay. The charging outlet and your device's built-in adapter are shown in parentheses. Given the adapters from the first example, your total number of arrangements that connect the charger to your outlet is 8. Second example, ooh, that's a lot. Oh my. 1920. You glance back down at your bag and try to remember why you brought so many adapters. There must be more than 1 trillion valid ways to arrange them. The heck? Oh my god. Oh. Hello, Harry. More than 1 trillion. Okay. This is going to require some dynamic programming, which is going to be difficult to explain. I think it's going to require dynamic programming. I think. Because the input size is only 97. Okay, it can't possibly be more than 1 trillion. It can't possibly be more than 1 trillion. Oh. I don't think it's more than 1 trillion. Okay, so why don't we... This is going to be difficult. Okay, this is going to require... I think it's going to require dynamic programming. But surely they wouldn't use something like that. Okay, actually, dynamic programming isn't that difficult to explain. So... Okay. Because like apparently on the about page it says that you don't need any experience with algorithms to solve these. But this kind of does require an algorithm, but it's a really simple one. Dynamic programming isn't that difficult. So maybe I shouldn't call it dynamic programming. Maybe I should call it splitting it up into different types of problems. Wait, this is concerning. This is concerning because the answer is 19,000 here. DP isn't really an algorithm. Yeah, I guess it's more like a strategy. Yeah, fair enough. Okay. Oof. Okay, we're gonna need to sort these first. I'm gonna do all the data processing at the beginning here. So, I guess we will joltages. Okay. Yeah, we're gonna have to do this. Okay, so we're gonna do some dynamic programming up to n. Actually, no, we should probably do a start and an end. Oh, hello, Annie. I don't. Okay, the key sounds so satisfying. I don't have a mechanical keyboard, but it still sounds nice. All right, so I'm gonna ignore the chat for now and just keep going. So dynamic programming, we're going to do the number of ways to go from a starting point to our device. So yeah, okay, we're gonna do that. All right. Yeah, wait. This may or may not be required. Okay, I think this makes sense. Okay, so we have an input. We need to find if the next one has an input of. Okay, I think this makes sense. This makes sense. Okay, this is confusing using I and index. I guess next index. There we go. Okay, while the difference is less than or equal to 3, we should do our sum. Okay, I think this is valid. We also want to check if index equals. There's only one way to do that. Okay, I think this is pretty simple. And then we just do dp0. Hopefully this doesn't run forever. It might. None, because we didn't return the answer. Very nice. 0. Why don't we? Because I don't think all these are getting called. Oh my god! I didn't increment next index. Still though, that shouldn't. Why wasn't that an infinite loop? Okay, you know what? I'm gonna print out. Wait, I don't. Maybe we can't start at 0. Yes, all that makes sense. Okay, let's look at our input. Our input. Oh, did we sort this? Oh my god, we didn't sort this. Okay, it's sorted. Index out of range. Interesting. Okay, why don't... Yeah, we have to make sure it's within range. And it's running forever. Why don't we implement some kind of LRU cache? LRU cache. And then this is basically just memoization. Oh yes, this is a core part of dynamic programming. You actually have to do memoization. Okay, so after that we got an answer. It's the right answer for someone else. God. Okay. Okay, I'm gonna take a look at the chat. Alright. The chat is overrun with people of a certain group and not people of not people who actually want to see the solution to the video. Which is fine, but you know. It's okay. Most of the views from people who want to see the solution to these puzzles come after the stream, you know? So, okay, let's figure out why this is true. Oh, I think I know. We have to start at 0. Okay, and that changes our answer to this. Okay, and hopefully this should work. I need to wait a minute. I think I already waited a minute. It's the right answer. Let's go. Okay, so now it's time to explain. And also this is going to be really hard to edit. So okay, let's... This is gonna be... I wonder what the subreddit is like. Like, people are saying, wow, I don't know how to solve this. Probably. I'll take a look at the subreddit later. But, okay, so... I think this is going to be pretty difficult to explain. I'm already going over time. What was LRU cache? LRU cache is basically a thing in Python where you can use it to cache the output of a function so that you don't need to evaluate it twice if it has the same input. So it's like a memoization table, except you don't have to actually implement it. It's a very handy trick. Okay, so I guess we should explain it. I think I might want to draw this out just to hang on. Yeah, I might want to draw this out. Code needed. Hello. Yeah, the code is in a GitHub repository. Actually, no. Should I just push it? I'll push it right now. I'll push it right now to the GitHub. All right. Okay, so it's now in the GitHub repository. The link to which should be in the description. So, yeah. Okay, you have it. Oh, okay. Y'all can see it now. It's already half an hour after the puzzle release, so likely all the solutions are already out. Okay, this is gonna be a pain to explain. I'm going to set up the page in OneNote first. So, all right. I'll see you in a bit. All right, so I'm back now. I think this requires some good old-fashioned diagramming on OneNote. Okay, so let's just do a small example first. And And I think we should do the example before I explain the overview. So let's get our input. Actually, I could just scroll up inside the terminal to see this sorted. So we're going to use a previous input here, and we're going to use a sorted input. Okay, so our input is 1, 4, 5, 6, 7, 10. I think it's 11, 12, 15. 16, 19. All right, so what we need to do here, what the problem is asking us to do, is we have all these adapters. We have a source of 0, and then we have an output of 22 in this example. And we want to create a chain, but we don't have to use all of them this time. We can leave some of them out. But they still need to go in increments of 1 to 3. So we're going to use a technique called dynamic. Oh, I realized you can't see some of this. But that's okay, because I can't see it either. So I know how you feel. All right, so we're going to use a technique called dynamic programming. And the idea here is basically like recursion, but smarter. And that's how I like to put it. So it's recursion, but smarter. And the idea behind recursion, but smarter is basically just to do recursion, but to make it smarter. So the idea is that we do recursion on, we have a function, and our function takes in an input. So for example, I'll just put in indices here. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So, actually, I should make 0 be the source. Okay, so, okay. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so our function takes in an input. Let's say it's 5. This means that we have completed the chain up to this point. So, for example, it might be like 1, 4, 6, 7. So we know we have a chain up to this point. This doesn't really matter. But we have a chain up to 5, index of 5. And this means our current adapter is outputting a wattage of 7. So our function is going to return how many ways we can connect the 7 to the 22. And how can we do that? Well, the only way to do it is actually to put a 10 next. So we want to call the function again on the 10. And this means that we've just have our source as a 10, and we need to get to 22. And how do we do this? Well, we can actually do this in different ways now. We can either have an 11, or we can start from 12. So we have 2 ways to do this. And from an 11, we call the function again on 11 to see how many ways there are to get to 22. We call it on 12. How many ways are there to get to 22? Let's say there's like 12 ways to get it from, I don't know, that's confusing. Let's say there's like maybe 3 ways to get it from 11 and 12 ways to get it from 22, from 12, starting from the sources to get to 22. So we add these together, and that gives 7. So actually, this means starting from 10, there are going to be 7 ways to get to 22, because we add up all possible next steps. And we can actually do this step further up. This means that for starting source of 7, there are 7 ways to get to 22. And this is just an example. It might not actually be 7. So our function takes in an input, and our input represents what current source we have, and then it returns how many ways there are to get to the final answer given our source. So the how we make it smarter is, for example, let's say we have 10. Actually, we have 10. 10 is going to call 11 as well as 12. So these I'll go back to 10. So 10, the number of ways to get to 22 from 10 is going to be the number of ways to get to 22 from 11 and 12 combined and added together. So that's all well and good. But what happens when we want to call the function on 11? We want to find out how many ways there are to get to 22 from 11. Well, we're going to have to call 12. So 12 is going to feed back to 11. And this means we're actually going to have to compute 12 twice. So we don't have to actually compute it twice. We can just compute it once and then reuse it. And the technique that this is often called is memoization, which means that we take a look at the given inputs, and then we can actually store them in memory so that we don't have to compute them again. And how I actually do this in Python is with a library called functools, using a method called LRU cache. And this basically just takes a function. If you write it directly before a function, it caches it as you run the function, and it stores it in memory so that if you run the function again, yeah, it's basically like a hash table. So that if you run the function again, then you will get the same output given the same input. Yeah, it just memoizes the outputs of the function. And I know switching between dark theme and light theme is probably going to be pretty disturbing for a lot of you. But there's no way I can prevent that. Unless I switch this to be light mode. So, oh my god. I might have to edit that out. Okay, let's go into the end screen. I'll be back in a bit. Alright, we're now in dark theme, so this should be more comfortable on your eyes now. It's pretty late. But, if you're watching this afterwards, hopefully it's also better. So that's the idea of memoization. Dynamic programming. It's recursion, but smarter. That's the essence. And if you want more detail, it's basically we define a function. It calls more functions. And then we do a memoization. This is memoized. That's the idea of dynamic programming. Okay. Yes. Okay, now it's time to actually get into the code. Okay. Remember that we said earlier a function is going to count how many ways there are to, given a starting joltage, to get to the ending joltage. And actually, for all dynamic programming implementations, we're going to need a base case. And our base case in this example is, our base case in this case is reaching the end of the joltage list. And reaching the end of the joltage list means that we've reached our device. And after that, we can just end it because there's one way to get to it. So again, our function is counting how many ways there are to get to the end given a starting source. And if we're already at the end, then there's only one way to get to the end, which is just to go there. Okay. Okay, now this bit. So we're going to need to count how many ways there are to continue. And the number of ways there are to continue, then let's go back to our example. I'm just going to erase all this. I should use a stroke eraser. Okay, and our function actually doesn't take in the starting source as an input. It takes in the index of that source. So, for example, let's say we're trying to compute 10. All right, we're trying to find dp of 10, and often these functions are just called dp, but I mean, maybe that's just me. But okay, so let's suppose we want to compute dp of 10, and the next bit over here is looking at future indices. So we're going to do a while loop. We're going to loop to the future. So currently index equals 6. We want to look at the other ones. So we want to look at index equals 7, and 8, 9, and 10, and so on. So we look at 7, that's 11. So we want to find dp of 11 because we can continue with 11. That's a possibility. And we can see that in the code right here. We add the possibilities for continuing onto our total because we're counting a total number of ways. So we're looking at all possible ways to continue and just accumulating them together. So index 7 gives source of 11, so we can continue with 11. We want to add that to our total. Increment by 1, our index is 8. We can also continue with 12. So we want to add that, the number of ways to do that, onto our list. For 9, that's 15. 15 is unfortunately out of our reach because we are currently computing DP of 10. An adapter of voltage 10 cannot connect to voltage of an adapter of voltage 15 because they're more than 3 apart. So we can end the while loop there, and this is the condition that we're checking. We're checking that the index that we're looking at minus our original source has to be less than or equal to 3 because that's the only way they can connect. Okay, and this check over here is just to make sure that our index doesn't go past the end of the list, so that we don't get like an index out of range, out of bounds error. So this is just like preventing errors. Okay, I'm gonna need more water soon. So do a while loop, just checking that the next adapter that we check is within range, and then we want to add up all the adapters that are within range, the number of ways they can get to the source, because those are the number of ways to continue. And when I said this is like recursion, this is kind of like recursion because we're taking a look at a parent and then we're looking at all the ways to continue, and this just builds out a huge tree. So that's the recursion bit, because we're looking at the number of ways to continue, and there's many different ways to continue. That makes a tree. I'm repeating myself. But the thing is, with dynamic programming, it's not actually a tree. It's more like a graph because some of the nodes are duplicated. So you can notice that if we take this out, this is going to take a long time to run. Oh, no. Why am I running git push? Okay. You can see it takes a very long time to run, even with a small input. Oh, no. Even with this is our big input. So you can see it takes like really long to run. And then you can see if we get rid of it, if we put it back in, memorization, we get our answer like super fast. And this is because we don't have to compute things twice, as I said. All right. That was the explanation for part 2. Really short code, requires a long explanation. Take a look at the code. Figure it out. Oh yeah, and at the end we just call DP0 because we're starting at index 0. Okay, so hopefully that makes sense. I tried to explain the code in more detail. I know a few parts might have been pretty confusing, and I apologize for that. So this video might have to be really heavily edited, and then I might have to make a new one. But I want to test out the YouTube editor, and you know, this is a stream, so I want to keep that like sentiment. Okay. So thanks for watching the explanations. Hopefully they made sense. If you want additional help, my Discord is in the description, and you are free to DM me if you want. But also, like, try to figure it out for yourself first, because I'm also a busy person. Okay, so the code is going to be in the GitHub repository, link to which is in the description. There's also a playlist for all the other puzzles. Links to that is also in the description. Yeah, timestamps. If you're watching this part, you don't need the timestamps. That's basically it. So you're free to leave now if that's all you're looking for. If you're just looking for the implementation and the explanation, all the dynamic programming stuff. But yeah, so thanks for watching. You can leave now if you want to, but if you want to stay, want to watch the rest of this video, the rest of this high quality content, I'll be just ranting a little bit. Okay, pressure's off. I'm gonna get a little bit of water. Yeah, so stick around. I'll be back soon if you want to hear me rant, but you probably don't. So I don't know. I just want to. Alright, welcome. We are back. The explanation is over. The main part of this video is over. But I just want to rant for a little bit at the end. So, no more pressure. I got my water. Okay, this is going to be over soon. So, in this puzzle, we saw that the algorithms are starting to kick in. I haven't done any previous years, but looks like algorithms are actually going to be a thing. Dynamic programming isn't that hard to figure out on your own if you don't know it, though, I guess. So, it does take a little bit of skill to know when to use it. I guess recursion, you would have seen recursion coming in this problem. And then, like, adding memoization is just a simple step on top of that, I guess. So, this is actually just one-dimensional DP, which isn't that difficult. So I guess it's not that hard. But I do see the algorithms starting to come in. And for the rest of it, this concerns me. Why is there... Oh, I see. Okay, so I said in this morning's video, the top is like your starting position, and you're trying to get through the forest on your toboggan. And this is the airport. The green parts are the airports. Yeah, and then this is the first airport over here. This is the second airport. And this, tomorrow, we're going to arrive at our destination. And this little dashed line is our trip. Okay, so that's why they made it spaced out. Cool. Also, I just want to reiterate, I am happy that they're not doing int code again. They're not doing that, those VMs. Like this thing, they're not redoing it that much. So, that's good. Okay, why don't we check out the subreddit? See what they have there. I don't know if I'm allowed to put this on YouTube, but okay, there's a lot of posts on here. Okay, interesting. Okay, so there wasn't much about today's input. So, today's puzzle. So, okay, well, that's pretty cool. It's getting close to an hour now, so I'll probably end the stream here. That's it for my rants, probably. Yeah. Okay, cool. Thanks for watching. This is the real end now. Goodbye. I will see you tomorrow, or maybe actually even the day after tomorrow, with day 11. So, goodbye. I will see you later. Thanks for watching.